Okay, welcome to week 6, lecture 2. We're going to take a look at some other plotting libraries in addition to Matplotlib that we talked about in the previous lecture. In this lecture, we're going to look at, to begin with, Seaborn. Not sure where the name came from. The conventional abbreviation that is used for Seaborn, which frankly, I don't know why this is true, is SNS. So you'll notice that in our example code here, we've imported Seaborn as SNS. Now, SNS is actually built on top of Matplotlib. And because we're going to be using some ND arrays and some data frames, I've also imported NumPy, pandas, and matplotlib.pyplot. We're also going to be generating some random normal, draws from a random normal distribution as well. So I'm importing random, which is a standard random number facility module for Python. So that's the basic collection of modules that we'll need for these demos. Okay. So some things are very similar to Matplotlib. Here we're creating X as an ND array of values from -pi to pi at 0.1 increments. And I'm computing Y as the sine of X. But this time, instead of just plotting those things directly, I'm going to construct a data frame for Seaborn to make use of. We're using the dictionary approach to building a data frame, so I'm going to have a radians column, and that column will be filled in with the horizontal x values, and I'll have a sine column filled in with the y values. The line plot that I'm creating here is going to be x versus y. Now, in Lineplot, x is a keyword parameter, and I'm specifying the column name within the data frame for that horizontal axis, as well as the column name sine for the vertical axis, and then I'm passing in the data frame, sine data, as my data, and this will produce the same plot that we saw when we were introducing Matplotlib. All right, so I guess it's up to you. Do you think it's easier to put this data into a data frame and then plot the columns out of the data frame? I guess generally speaking, if you already have a data frame that has columns of values, then it's very easy using Lineplot from Seaborn to give yourself a plot of some horizontal axis versus some vertical axis. Okay. This time we're plotting a straight line, y equals 2.5 of x, and I'm creating an ND array of x values going from 0 to 10 with intervals of 0.2 and setting y to 2.5 times x. Once again, setting up a data frame using the dictionary notation, so I'm going to have an input column, which is going to be my horizontal values for x, and an output, which is y. In Lineplot, I'm setting my keyword parameters, x, y, and data, and here's what that looks like. If I can bring my editor forward, there we go. Okay. Okay, so very similar kind of thing here, except we're plotting a line instead of a sine wave. Save this and run it. And poof, there is my line. Okay. Close that. Now, we're going to take a look at adding noise to this plot and then calculating correlations and whatnot. Let's build up to that. Okay, so I'm going to continue using the same x and y that I started with. I'm going to make a copy of y called y2, and I'm going to modify all of the values within I2 by adding some Gaussian noise. Okay, here's the random module that we imported, and I can get a random draw from a standard Gaussian. Well, this isn't standard. This is a Gaussian distribution with a mean of -3 and standard deviation of 5. Gaussian is same as normal distribution. Okay, so y2 is therefore a noisy copy of y with a lower mean value than y and scattered, normally distributed around that lowered value of y. So, given this y2 that I've now created, I'm going to create a third column in my data frame, my data, called actual readings. Okay, we're imagining that these are actual readings that I've taken from a temperature sensor or wind speed sensor or whatever. And the error, therefore, between y and minus y2 is going to be my fourth column. Okay, so now what have I got? Let's back up. I've got my input, which doesn't have any errors in it, and I've got my expected output, let's say, which also doesn't have any errors in it. All right, so the input is just from 0 to 10 at steps of 0.2, and the output, the expected output, is 2.5 times the input. Now my actual readings from my sensor are given by y2, which is a noisy version of y, and then my error, the difference between the expected value and the observed value, is y minus y2. And now I can create different line plots. I'm going to do the input versus the output again. That's going to be my straight line. And I'm going to add another line here, which is going to be the input versus the actual output. And that's going to be a jagged line. So let's have a look at that. Okay. Okay. So my x is as before. My y is as before, 2.5 times x. My data frame starts out with input and output columns. I'm going to make a copy of y called y2 and add Gaussian noise to it and create these two additional columns in my data, the actual column and the error column. And then I'm going to create these two line plots that we can see together in the same plot. And because I'm using idle, I have also had to throw in plot.show. You wouldn't need to do that in Spider or other IDEs necessarily. Let's run this. And there we are. Okay, so there is the, let's say, the predicted result, the expected result in blue, and the jagged orange line is different from the expected result. Now, next up, let's take a look at computing the correlation between the actual data, the jagged orange line, and the input. And we know that that's not going to be a correlation of 1. I shouldn't have closed that window yet. I guess we can just back up and see it in the notes. We know it's not going to be a correlation of 1, because if it were a correlation of 1, the orange line would be exactly parallel to the blue line. But here the orange line is, jaggedly moving around the blue line. But it will be a positive and fairly high correlation, probably. And so we're going to get that correlation coefficient as a string so that we can set as our title for our plot that this is a linear regression with the computed correlation coefficient. Okay? So, all right, so this is a standard NumPy correlation function. My data sub input is a series. My data sub actual is a series. And here I'm computing the correlation between those two series. Regplot is going to give me a regression plot of the input versus the actual based on my data. And that is going to give me a confidence interval band around the plot, which should look like so. Let us confirm that that's what we get. All right, so I'm going to comment out the jaggedy lines or jaggedy line, and now we're going to put in the correlation coefficient in the title with our confidence interval. And there we have it. Okay. Okay, so the correlation, as I said, is less than 1, but it's still relatively high and positive, of course. So we got a correlation in this case of 0.81. I did want to just mention, by the way, if you're comparing these plots, that the random number generation is going to be different each time we run a sampling from the random a sampling of random numbers, because we didn't reset a seed to any specific seed value. So the plot that I have produced in real time here looks a little different from the plot in the notes. All right, the plot in the notes is what Professor Barrett got when he was first testing this code, and each time I run this code, I'm going to get a slightly different plot. Okay, so in fact, let me just for gags, let me do that. Notice that we've got a point way down here below -10 and another one way up here above 30. Let's see if I run this again, if I can see those two obvious differences. And yes, okay. So I no longer have anything that's below -10. I no longer have anything that's above 30. So this is a different collection of random draws from the Gaussian. Okay, and you'll notice the regression line does start at -5, which is the offset from our standard normal, the offset from our Gaussian noise. Okay. All right. Here is a regression plot in which we're fitting a parabola instead of a line. Let's give that one a shot. Okay, so instead of doing a linear regression, I've thrown in this additional argument, order equals 2, and I'm going to create a green line rather than a blue line. Now, depending on the particular data that I get, my parabola may look very much like a line. In the example in the slides, you can see that there's something of a curve going on there. But when I have tested this myself, very often the parabola looks pretty close to a line. So let's see what happens here. Okay. There we go. Yeah. All right, so that is a parabola, but it looks pretty close to a line, just because of the data that were generated here. Let me try it again just for gags, see if we get something that's a little more obviously curved. Well, I don't know. Maybe that's curved down just a touch. Anyway, okay. So there we go. I can produce scatter plots of all the columns versus each other by asking for what's called a pair plot. And let's give that a try. And this is going to be very large on my screen initially. Here is what it's going to look like. When I squeeze mine down so that you can actually see it in my video, it's going to look a lot uglier than what's in the notes. Okay, so we've got the same X, the same Y, noisy Y2, input column, output column, actual column, and error column. And this is going to give me scatter plots of all the pairs. Now, input versus input, output versus output, actual versus actual, these are just going to be histograms, but the other ones are going to be scatter plots. And I get this big plot, which you can only see a little part of. Let me try to shrink it down vertically so that you can see more of it, but it's going to look really ugly. Okay, so there we are. Okay, now these, for input versus input and output versus output, I didn't specify the same number of buckets as were created for the versions of these in the notes, and so they look slightly lumpy here. That's just an accident. It really is. They really should be level. And then for the actual and the error, of course, we do have noise going on. Okay. All right, now we're going to take a look at a different data set, which has to do with tipping data in restaurants. Let me comment out this code. Okay, and you can go out to the web and you can obtain this tips.csv file on this GitHub website. Each line in here, and I think there is 250 or 255 lines, we have the total amount of the bill, the total amount of the tip, who the payer of the bill was, whether the pair was a smoker or not, which day of the week it was, which time of day it was, lunch or dinner, and what the size of the party was. Okay? So, the size of the party can be, 1 to 5 or whatever it is. All right. Now, the entire file, as I said, is quite long. Let me just, for gags, quickly show you the entire file. Okay. Let me shrink this window down a bit. Okay, so here's the top of the file. And we see that the first several lines are the first 5 lines are the same as the lines in the course notes. And as I scroll down, you can see it looks like the largest party that I have in here is 4 people. I've got some singletons, lots of 2s, a few 3s. Here we have a party of 6 people. Okay, so mostly 2s, some 3s, lots of 4s, some 1s, some 5s and 6s. Okay, and altogether there are 245 lines of data in this CSV file. Okay. So what we're going to do is, and here, in order to avoid having to reread the CSV file over and over and over and over again, I've just collected together all of the code on the next several slides into one chunk, and we're going to go through and talk about the pieces piece by piece in here. So the first thing we're going to do is read the tips.csv file into a data frame called tips, and then we're going to use the head method to display, by default, the top 5 lines from that data frame. Notice here that I have an input function. Press enter to continue, so that will pause execution at that point, and we'll be able to go forward in the notes and look at subsequent descriptions in the notes. All right, so to begin, I'm going to run this. And, okay, so the CSV file was read into the data frame, and I executed head. Here are the top 5 lines from the data frame, exactly as shown in the notes. And now I've got my input function, which has paused the execution. We're going to create a facet grid so that I can aggregate information based on categories, based on the sex of the person paying the bill, based on the day of the week, based on the time of day, based on whether the person is a smoker or not. And here we're going to do a rel plot. That is a relational plot on which the horizontal axis is going to be the total amount of the bill paid, and the vertical axis is going to be the tip. All right, so if you have ever worked as a server, you would like to see those tips be around 20% of the total bill. So we would like to see a line going up roughly at 20%. 15% is okay, less than 15 and you're a cheapskate. Now, we're going to produce different plots aggregated by time. So we're going to have one plot for dinner and one plot for lunch, because those are the only 2 different time values that we have. The color and style of the individual data marks are going to be determined by whether the person is or is not a smoker. And the size of the data mark on the plot is going to be determined by the size of the party. Okay, and you'll see on the plot what that means. And then the data, of course, for all of these attributes, total bill, tip, time, smoker, style, and size, are going to come from the columns in the data frame. So let me hit enter so that we can see what this relational plot does. And here it is. Okay, so we have two separate plots aggregated by time. So we have a plot for the dinner crowd, and we have another plot for the lunch crowd. On the horizontal axis, notice that we have the total bill, the total amount of the bill. And on the vertical axis, the total amount of the tip that was paid. Now, smokers, non-smokers are in blue circles, and smokers are in red or orange crosses. And notice the size of the dot here indicates how many people there were in the party. So we have parties as small as one person, up to parties as large as 6 people. So, for example, this blue dot right here is a dinner time party. Looks like it's at least 5 people. It might be 6, maybe 5. And these people spent $50 and left a $5 tip. Terrible. 10% tip. Cheapskates. And these people were non-smokers. Now, look at these smokers up here. Here we have a small party of smokers, maybe 2 people it looks like. And wow, lavish. They spent $50, but they left a 20% tip. They left a $10 tip. So good for them. So more or less, it looks like this line is around, between 15 and 20%. We have some cheapskates who aren't leaving enough, and we have a few people who are leaving a lot. Here's someone who spent $7 and left a $5 tip. Okay, cool. And then for the lunch crowd, we have fewer people. And a similar style of plot. Not quite so many cheapskates at lunch, it looks like. Okay. So that's aggregated. Jeez. That is aggregated by time. Next up, we're going to have the aggregation by the gender of the person paying the bill. And, okay, so this time we're creating different plots based on the sex of the payer rather than the time of day. And look what we find here. Okay, so a lot of, at this restaurant, a lot of men paying bills compared to women. It looks to me, though, like men are cheaper than women as far as tipping on average. Okay, so it looks like this primary line here is around 20%. And it looks like the primary line here is close to that, like, I don't know, maybe 18% or something like that. But we do have a much larger chunk of cheapskates over here for the men, it appears to me. Okay, so I have no idea whether this data is real or made up. But in any case, so that's a couple of examples of relational plots. All right, in this next example, we're doing what's called a factor plot. And we're computing a new column, tip percentage, which is going to be the tip amount divided by the total bill. We're going to display the top 5 lines of that modified data frame with that additional column added. Let's have a look at that data. Okay, so here is the modified data frame with this tip percentage column added. Goodness me, we've got someone who left a 6% tip here. Yikes. And when I hit the enter key, okay, I get yelled at that factor plot has been renamed as CatPlot, category plot probably, and that the original name will be removed in some future release. So we can either hop to it and change factor plot to CatPlot, or we can just ignore that thing for now. And the plot is very large. Let me shrink it down, which in turn will make it ugly, so that you can see it in my video. Okay, so this time we've split our plot into 4 quadrants. We're plotting day versus tip, and let me make my displayed plot a little narrower so we can see the tip on the left side. Okay, so the days that the restaurant served meals were Sunday, Saturday, Thursday. That's on the horizontal axis, the x-axis. And the tip amounts are shown on the vertical axis. We are categorizing or creating quadrants based on time for the rows. Notice that the top row is for dinner time, and the bottom row here is for lunch time. The columns are categorized by smoker. So in the first column, we have non-smokers, and in the second column, we have smokers. Now, if we had, 6 different times and 4 different categories of smokers, we would have had a facet plot of 24 facets rather than these 4 facets that we have in this case. The kind of plot we're producing here is a bar plot. And notice that these bars, some of the bars have these black lines in them. Some of the bars are missing. Some of the bars don't have black lines. Let me describe what's going on there. The data that we're using is those records from the tips data where the tip is less than the total bill. All right, we're computing tip divided by total bill, and that has to be less than 1. I didn't happen to notice any cases where the tip was greater than the bill, although there may have been some of those. So we're probably selecting most of the data in any case. All right, so let's talk about the results. So as I said, we have days on the horizontal axis, and the restaurant is apparently only open Sunday, Saturday, Thursday, and Friday. So we've got 4 days. Tips vary from $0 up to $4 for the data that we have selected. Okay. Now, when we don't have a column at all, it means that that there were no people fitting that category. So it turns out, if you look at the actual data, there are no lunchtime guests on Saturday and Sunday. So presumably the restaurant is closed on Saturday and Sunday for lunch. For dinner, on Thursday, during the period of time of this data set, there apparently was no smoker who was a paying customer on any Thursday during the period of the data. Now, as far as the black lines are concerned, the black lines show the range of tip values for these different categories. So, smokers who had dinner on Sunday left this range of tips. The average tip is what's shown by the top of the blue bar. Okay, so you'll notice in every case that the black line goes entirely through the bar because the top of the bar is the average, and there is variability around that average. All right. In this particular case here, the green bar for non-smokers at dinner on Thursday, the reason there's no black line is because there was only one non-smoker who had dinner on Thursday. And so that one person's tip is both the range and the average. All right, so that was that was a bit of a lengthy description, but that's what that plot is all about. Okay. Here we're going to take another look at a box plot instead. All right, kind is box here rather than bar. Let me close my bar chart, and that should display the box chart. There we go. I'm going to have to squeeze it down just a little bit and drag it up so that you can see it. So, what does it all mean? Okay, so the horizontal axis here is the tip percentage, and we can see that in the plot. So the tip percentage here, it's really a fraction, is from 5% up to 40% here. Then the vertical axis is the day. And so our days here are Friday, Thursday, Saturday, and Sunday. We are only looking at data where the tip percentage is less than 0.5, but that probably includes almost all of the data. And to understand what these box plots are saying, the vertical bar in the middle of each of the boxes is the median value. So the median tip percentage on Sunday was around, looks like around 17 or 18%. The median tip percentage on Saturday, Thursday, and Friday all look like about 16%. Okay? So I guess if you're a server, you want to work on Sunday to get those extra couple of percentages. Then the edges of the box, the lower edge to the upper edge, are from the 25th percentile to the 75th percentile. So this is what's called the so-called inner quartile. Half of all the tip percentages fall in the range from the lower edge of the box to the upper edge of the box. Then to the left and right of the boxes are what are cleverly called the whiskers, which show 1.5 times the width of the inner quartile, unless 1.5 times the width gets us to a point that's below the bottommost value that is actually in the data set. All right, so on Sunday, apparently the lowest tip percentage that was actually given looks like it was around 7%. So we can't go below 7% if that was the lowest value that was seen. On the right-hand side here, you'll notice that this whisker is 1.5 times the width of the, well, approximately 1.5 times the width of the inner quartile. It may be just a hair narrower than that, because, again, the vertical line at the end of the so-called whisker is reduced to be at an actual observed value. So an actual observed tip value appears to be around 28% or so. And then these black diamonds on either side of the whiskers are outliers. So somebody gave, looks like around a 42% tip on Sunday, which is way outside the inner quartile and the whiskers. All right, so that's that's a lot of noise. Basically, the vertical bar is the median value. The box itself shows the middle half of values. So 1/4 were below and 1/4 were above the box. And then the whiskers show kind of the spread. And these diamonds represent values that are just way outside the I don't know what you might call the usual expected range or whatever. There is a really good video that explains this in probably more detail than you want to know. Here is the URL for that video, but if you just Google for Seaborn Box Plot Kimberly Fessel, she has a really excellent video that describes how these box plots are actually constructed. I think that they're easier to understand intuitively than they are to understand technically. Okay, so half of all the action is in the boxes, and the vertical bars are where the medians are located. All right. Okay, so that is Seaborn. There's a couple other ones here that I'm just going to say out loud, and if you're interested, you can look them up. Plotly is yet another module that you can download and use. It's not, I guess it has some fancier kinds of plots compared to Matplotlib and Seaborn. Well, okay, so we'll call it a day there. You can certainly look into Plotly if you're interested. Okay, take care.